I'm Christian Reddy, your friendly neighborhood astronomer. I want to thank everybody for joining me. It looks like I went live, but not here on this screen, so I'm getting the hang of this. I'm using a new streaming software. I've also relocated down to where I normally film my videos to give it just a little bit more ambiance, and I am now hearing myself on my own. You know, this is just the sort of thing, once you get the hang of this and you know what you're doing, it just gets so easy. Until you know what you're doing. I don't know what I'm doing, so it's great to see folks dropping by. Let me just say hi to Peter Quinn. Good to see you, man. And Aaron Wilson. Oh, lovely to see you. Matt and Matt from Create You. You know, not exactly an astronomer, but a very inspiring fellow nonetheless is Matt. He just has a wonderful channel at Create You. And Andy Law, you're telling me that my audio level is low. I'm going to see if I can improve it now. Let me see. I'm just a tad quiet. Okay, no problem. Give me just a moment, please, as I adjust fire here. Let's see. Okay, and I see Maslow from Towson and Pusa Studios. Wonderful, good to see you. Let me continue to adjust my audio here, and you just tell me if you're hearing me clear and loud. I'm going to have a little bit of a quick play here with my settings. Oh, that is better? That's wonderful to know. That's great to hear. If there's anything else I can do to improve it, just let me know. Maybe it's still coming in a little bit too low. Maybe it's just fine. That is up to you. Please do let me know. But I'm seeing that's much better. Thank you, Peter. Hello, Robin. Good to see you. Welcome to Launchpad. Welcome to Launchpad Astronomy. I'm Christian Reddy, your friendly neighborhood astronomer, and I'm live streaming. This is wonderful. And the reason I'm doing this, for the folks just coming in, the reason why I decided to do this today is because next week I'm giving my first celebration of knowledge. Some people call it an exam, but I like to call it a celebration of knowledge because why not, right? We're here to learn stuff. We're here to do things. We're here to explore the universe. Let's celebrate what we know. How wonderful is that? So I thought I would offer this live stream as kind of like an informal review session, but not just for the exam, but for anything that you want to talk about. Your questions, my answers, or at least my best attempts at answering them, because there are so many things that we don't really know about the universe. But what I thought might be kind of fun is, love the Halley's Comet poster. This is my Halley's Comet 1986 commemorative plate. I was there when it came by. I didn't see it, but I got a plate, so at least I got that. Anyhow, and how's it going? Has Mike Pluto Killer Brown got going on finding Planet 9 or 10? Well, they're still looking for it. Here's what I do understand. They did an observing run back in December of last year, which was their very best observing run in terms of the weather, in terms of the quality of the data. Absolutely top-notch. They didn't, nothing immediately jumped out at them. But they also had another observing run scheduled for, just a couple of weeks ago. So they went ahead and did that. That apparently had a lot more weather problems. So it's very possible it could be sitting right there in the data just waiting to be discovered, but so far they haven't announced anything just yet. They have, however, published a really cool review paper, which is just talking about the entire Planet 9 hypothesis, the entire story of how they came to think it was there and why they are still very convinced it's there. It's tremendously exciting. I hope it's there because it would explain so many things, so many very weird and different observations about our own solar system that we really don't have any other explanation for. And it's always wonderful whenever there's an explanation for something that not just explains one thing, but explains a wide variety of observations. And so we're hoping that Planet 9 is there because it explains it quite well. So how's everybody doing? Carolina Rodriguez, what is going to happen with Planet 9 and Earth? Okay, well, what's going to happen with Planet 9, if it's found, what will happen is that they'll announce that they found it. How that will affect Earth, it won't. it would be a planet that is orbiting probably at around 300 times the distance from the sun as Earth is. So 300 astronomical units, or 300 times the Earth-Sun distance. So that means, to put that into some context, Neptune is 30 astronomical units from the sun. So Planet 9, if it's there, would be, 10 times farther away from the sun than Neptune? So how does Neptune interact with Earth? It doesn't, and neither would Planet 9. It would just be a really cool discovery to understand how things are working in our solar system. So let me pop my experience reading devices on. So, nice plate, Christian. Have you ever eaten food off of it? No, I have not, David Sims. I have merely commemorated the last time Halley's Comet flew by. I'm hoping I'll get another plate when it comes by again. So I'd like to see it come by at least 2 more times. So what, it's a 76-year period. You know, if I get my 10,000 steps in, no problem. Should be able to get that. So Gary Freeberger is saying that it might be smaller than they thought. You mean Planet 9? Yeah, they did talk about this. Their estimates had been initially kind of wide. First, it was 5 to I think 12 times the mass of the Earth. Then they revised it, I believe, down to let me see here. What do they revise it down to? About 8 to 7. Now I think they may be going as low as 5 Earth masses. So quite a bit less massive. But that's fine, because what that would do is that would put this planet well within what's called the super Earth category. So there's 2 kinds of exoplanets that we find everywhere in all of the other planetary systems. Well, actually, there's a whole range of sizes, but the 2 most common sized planets are either super Earths, in other words, they're a little bit larger than Earth, or mini Neptunes, they're a little bit smaller than Neptune. Planet 9 is thought to be a mini Neptune, but maybe it is in fact a super Earth. So that's kind of cool because that would give us our very own super Earth, and we could be just like all the other planetary systems that we've discovered so far. So Pusa Studio is asking, are there more planets in our system, solar system, that we don't know about, or can we say for certain at this point we know them all? No, Pusa, this is what we're talking about. This would be a new planet right here in our solar system, far beyond Neptune's orbit. But this would be, there's really good reason to believe it's there, but nothing will demonstrate that it's there until we find it. So this would be a real, legit, big, major planet. There are undoubtedly many smaller so-called dwarf planets. These are objects that look like a planet, smell like a planet, taste like a planet, but they are not massive enough to clear out the orbit. So in other words, they could be orbiting the sun, but there could be other objects with about the same mass following along in the same orbit. Every other planet, Earth, even Mercury, has enough gravity to either absorb or eject every bit of debris that shares its orbit. Pluto and Eris, Makemake, Haumea, Ceres, I know I'm forgetting at least 1 or 2. Anyway, there's loads and loads of these so-called dwarf planets out there. We expect to find many more. So how many more actual planets there are in terms of massive enough to clear out their orbits? Well, right now there's very good reason to believe that there's at least 1. There may be another. And I was actually thinking about doing a video about this, but I haven't yet. But basically, the idea works like this. There is, if you look in our Kuiper belt, okay, so everything I've been talking about Planet 9 is way beyond what we traditionally think of as the Kuiper belt. By Kuiper belt, I'm referring to the region beyond Neptune out to about 50 astronomical units. So between 30 and 50 astronomical units from the sun. And if you look, you'll see there's all kinds of debris there. We actually just flew past one of those bits of debris called Ultima Thule, which was just an exciting activity in and of itself on New Year's. Well, anyway, what we found is, or what some astronomers have found rather, is that there appears to be a slight warp. Okay, so in other words, if you have the plane of the solar system, all the planets are following along the plane, there may be some little bit of a warp. In other words, some objects are kind of scattered above the plane and their orbits are slightly inclined. And some astronomers looked at this, people who specialize in studying the Kuiper Belt. Sorry, I'm shaking my camera. Try not to do that. And it's they've determined that there is this warp. Here's where I'm going with it. They ask, well, what can cause this warp? Why would these objects, obey this slight inclination? And they found that a Mars, a body with the mass of Mars would do the job. Now, they're not going to go so far as to call it a planet because this object would not have cleared out the orbit, but it would definitely influence the orbits of everything else. So if you accept a slightly more generous definition of the term planet, and instead of insisting that it must clear out all of the objects in its orbit, and instead say that, well, if this object can dynamically influence all of the objects in its orbit, then we can consider that a planet. Then we could say that, yes, there could be a planet 10, about the same mass as Mars, somewhere in the Kuiper Belt, maybe out to about 40 astronomical units from the Sun. Remains to be seen, of course. That's in some respects, it would actually be a little bit easier to find this planet 9 because of the dynamic, because it's so much farther away from the Sun that it's much easier to ignore the effects of Neptune and all of the other planets. When you get closer to, when you get in the Kuiper Belt proper, yeah, Neptune can start to play a role. So it's a little bit harder to tease out whether or not you're seeing an effect induced by a planet or if it's some other phenomena that we haven't been creative enough to come up with yet. So that's a possibility. Let's see. So Jerry's asking, does that mean clearing out orbit definition discriminate against planets with large orbits? No, I don't think it would necessarily discriminate planets with large orbits. Again, even planets on very large orbits, let's consider the Planet 9 hypothesis. When you have an object that's at about 300 astronomical units, excuse me, Planet 9 would be taking up an orbit and it would have definitely affected the orbits of everything else. And so while there would be like an intersection of these Kuiper Belt objects, if you see my video on Planet 9, or I did 2 videos on Planet 9, but I talk about these objects that come in around the Sun, and they're all kind of clustered together. All these orbits are kind of all fanned out in the same direction. And then when you run through all the dynamical models and you plug everything into a computer, you find that there is a, oh gosh, wow, super. Okay, hold the phone. I just got my first super chat. No, I'm sorry, but second, thank you, Neil, for, oh my gosh, you're a real estate whisperer. Thank you so much. Christina Smallhorn is your real estate whisperer. Check out her videos on her channel. Anyway, where was I? Oh yeah, just talking about another planet in our solar system. So when you have these objects that are kind of fanned out, okay, and you have Planet 9 that appears to be responsible for it, is Planet 9 clearing out the orbit, its orbit? The answer is obviously no, it's not, because those other objects are intersecting Planet 9's orbit. Okay, but there's no question that Planet 9 is dominating its orbit. It's the dominant object in its orbit. Why? Because all these other outer Kuiper Belt objects have just completely done a sir, yes sir, and they're staying in a what's called a locked resonance with Planet 9. Okay, wow, I'm getting a lot of super chats. You guys are super generous. Thank you. God, what, £9.99 from Crypto Cruising. Make this the first of May live streams. Many live streams. You got it, buddy. I'll be doing this from here on in because now I found a streaming solution that does not destroy my computer. Yay! And Matt from Create You, super chat for $9.99. Oh man, maybe more of a history question. Is there validity to the thought that ancient Mesopotamia was more aware of our solar system than we were in the Dark Ages? If so, what happened to this knowledge? Man, that's an interesting question. That really is an interesting question. Well, it it is very clear that the ancient Mesopotamians and Babylonians and Sumerians all kept very accurate, very carefully written down records of the motions of celestial bodies. They were really keeping track of this stuff. So it is very likely that, well, it's not that they knew more about the solar system than we did in the Dark Ages, because even though during the Dark Ages, there was definitely seeking knowledge about the universe was really frowned upon by the church, who, by the way, were the government in those days. So that's living under a theocracy for you, right? But they were nevertheless, there were still some very talented astronomers. So I guess to really answer your question, Matt, it depends on how you define well-known, right? If you define well-known as well-known among the people, it may be possible that the ancient civilizations had a better, broader knowledge. During the Dark Ages, that knowledge probably would not have filtered out to the masses quite so much. So I don't really have a direct answer, but that's a very interesting question. Let's see. I believe we are smarter then than we are possibly now, says Pusa Studios. Wow, where are we smarter then? Thanks to YouTube, we have more people believing in flat Earth and conspiracies and so forth. That clearly is not doing much to increase our civilization's IQ. Part of why I have this channel is to help make America, but help make Earth smart again. And I'm not saying this is the only place to do that. As just one of many, but hey, it's a great universe. It's definitely worth talking about. Hi, Rike Hide. I'm loving this. Hello from Brazil. Hello, and I really hope I pronounced your name correctly. Rike, thank you so much for joining. It's wonderful to see you. Andy points out the Mayans. Yes, exactly. And Leah Weaver. Oh boy, one of my students. Hello. Okay, so her question. Okay, because I'm gonna have a policy on this live stream. If you are a student of mine, then your questions go right to the top of the queue, provided I can keep track of them. So I'm now going to address Leah's first question because we have our first celebration of knowledge. Let's see what she says. Can I buy extra credit points for the first celebration of knowledge? Okay. Thank you, Leah. Oh, that's wonderful. Thank you so much for that question. Thank you. Thank you. That's awesome. Yeah. Oh, and by the way, students, the super chat stuff, you're paying the biggest super chat price. It's called your tuition. So you don't have to be paying me. Thanks so much. But Leah Weaver, that's awesome. So what else can we talk about? I mean, I did want to talk a little bit about, the title of this was called How the Sky Works. And that's inspired for two reasons. Number one, I'm giving a test next week, a celebration of knowledge. I'm giving a celebration of knowledge next week, which entails the first part of our class, which is on the sky. Also, number two, because one of my good moderators here, Crypto Cruising, was asking about talking about this stuff. Hang on a second. Robin wants to know how much will be covered on Greek astronomy. How much will be covered? I mean, there'll be some questions that talk about what the ancient Greeks understood. Let me kind of switch gears here and talk a little bit about this particular question. Hey, folks, I'm not expecting you to memorize dates. I'm not expecting you to memorize the names of people. What you should be able to understand is, how they understood what they understood. How they understood, for example, how did they know the Earth was round, right? So we could talk about that if you're not sure. We could certainly discuss that. How did they know what the circumference of the Earth was? So that's the kind of stuff we want to think a little bit about. And okay, I'm just scrolling back up here through my so Robin, I hope that answers your question. Don't try to memorize dates and names. That's less important than understanding what they understood and how they came to understand it. Okay? All right. Okay, I see one here. So hello, this is Rachel. Oh, wait a minute. I've got this. I've got this little thing here I can do. Oh, this is cool. Look at this, and it's right over my face. All right, let's see here. Hello, this is Rachel from Astro 161. Could you talk about bound orbits? How bound orbits become unbound? Yes, Rachel. Let's go ahead and discuss that because that certainly is relevant, right? So if you want to give me a second here, I'm very much a show don't tell type of person, and what I can do is just bring up a couple quick slides. I'm not going to do a full lecture here, okay? I'm not going to don't worry about that. I'm not going to get that far in the weeds, but just by way of a very quick review, because understanding how orbits work is really key for understanding how everything from the moon goes around the Earth to how we get spacecraft into orbit and all that kind of stuff. So what I'd like to do, if you'll bear with me, is just bring up those slides so I can show it to you rather than try to tell it to you. So the first thing to think about, and I'm going to switch over here to my let's see, to Keynote. Okay, so hopefully you are seeing my slides, and to help visualize this, remember we're going to start with a rocket on the Earth. Okay, and you'll see it's kind of there at Cape Canaveral, Florida, if you look really closely, and we're going to launch our rocket. Okay, so up goes the upgoer rocket. All right, and now the rocket goes into orbit around the Earth. Okay, so this is an example of a bound orbit, and the bound orbit is an orbit that is going to come back in on itself. It's going to come around, right? It's closed. In other words, it's if we just let the movie play forever and ever and ever, this thing would just circle the Earth forever and ever and ever. And the way you can tell whether or not an orbit is bound or unbound is this value where it says E equals 0. That is a measure of the orbit's eccentricity. In other words, it basically tells us the shape of the orbit. So in this case, we have a perfectly circular orbit. It has an eccentricity of 0. But let us consider what would happen if we were to burn the rocket engine again. Well, now the orbit is still bound, right? It's still coming back around the Earth and will continue. But what we've done is we've elongated the orbit, or rather we've increased its eccentricity. So its eccentricity is now greater than 0, but it's less than 1. And remember, there are no units for eccentricity, right? This is not measured in kilograms. This is not measured in feet. This is not measured in dollars. This is not measured in packets of soy sauce. This is strictly a number. But if it's between 0 and less than 1, we call it a bound orbit. However, if we hit the rocket again, right, we burn the rocket again, we can now change that eccentricity to greater than 1. This means the orbit's unbound. In other words, this rocket is not coming back. So if you find yourself on an unbound orbit, okay, you're literally leaving Earth behind in the rearview mirror, right? So that's escape velocity, right? That's how you change. In other words, when you can build up enough velocity that you can change from this bound to this unbound orbit, you're out of here. You're gone. You're a dot. See ya. Not coming back. So how fast does that have to be? That's got to be about 40,000 kilometers to escape Earth's gravity, or if you prefer, 21,010 miles per hour. So this Tesla is the fastest car in the world. Okay, so a quick recap here: bound versus unbound orbit. Again, if your eccentricity is less than 1, cool, you're bound. If your eccentricity is greater than 1, you're on what's called a hyperbolic orbit, and that's unbound. In other words, you're not coming back. And so you may wonder, well, what happens if your eccentricity is exactly 1? Well, now you're still in an unbound orbit. It's just that now the orbit takes on what's called a parabolic shape. And for our purposes, it's the same thing. The angle at which you're going to depart Earth is going to be a little bit less. It's going to be a bit more shallow. It's almost like you're going to be continuously, almost but never, ever really turning around and coming back. Just kind of go all the way down. So that is, get rid of my Discord there. Okay, so that is that's how we do our bound versus unbound orbits. So I hope that helps you, Rachel. Let me know if that did not address anything, but I'm more than happy to talk about that. Let's see. I want to, let's see. Can I just want to make sure I'm not missing any other questions from my students. Show, don't tell. Unexpected Rush Presto reference. Right on. Yeah, okay, cool. Let's see. I just want to make sure that I'm not missing another student question. If you are asking a question, okay, I think Rachel Talbert's asking. So let me go back here, make sure I'm getting it right, doing right by Rachel here. Hang on. Okay, so Rachel's asking. Come on, I can drag this on, right? I can drag the thingy. Okay, so the first bound orbit shown by that diagram is circular due to the eccentricity being 0. Bingo. Yes, exactly. An orbit with an eccentricity of 0 is by definition a circle, right? And the reason why is because, well, there are two foci to an ellipse, right? So if you bring the two foci together, you have no longer two foci, you have a center. So you have a circle, right? Okay, cool. Let's see. And I, for one, welcome. Oh, yeah. Babylon 5, Peter Quinn, Londo, and I, for one, welcome our new shadow overlords, Mr. Lorden. Oh, gosh. Let me see here. I'm just double checking, making sure I'm good to go. Okay, so let me go ahead and rummage through a couple of these other questions. I just want to make sure I'm not missing your questions because I'm here as your friendly neighborhood astronomer to discuss them. I believe somebody mentioned, okay, so Harley says, my definition of orbit must be wrong. I thought it meant going around something. Unbound orbit doesn't make sense with that definition. Well, you're right, Harley. It is a very different kind of orbit. It's a new definition of orbit. We're simply talking about orbits with eccentricity that are greater than 1. Fun little fact, if you do escape Earth's orbit, in other words, if you break free of Earth's orbit, if you've achieved 25,000 miles per hour and you've escaped Earth, there is one little problem, and that is you're still in orbit around something, and that something is the sun. So hey, I'm getting a little feedback from Hybrid Steel. Only gripe is volume on mic. Rest of it is perfect, mate. Hey, cool, thanks. Okay, so improve my volume. Does this improve anything? Is this a little bit better? Kindly let me know if this is getting any better. So, Andy says, oh, wow, Christian digs Rush and B5. How to work out how to cancel something so I can fund this. Oh, bless your heart. Rush is cool. I'm actually a lifelong Deadhead, born and raised on the Grateful Dead, so... All right, what else do we have? So, yeah, give me a shout, give me a thumbs up, down, meh, on the mic. Okay, Pusa, got to go now, unfortunately, but we're so happy to have... So you started live streaming. Thank you, Pusa. And by the way, everybody, if you want to check out Pusa Studios tonight at 7 o'clock, they go live and they talk about other YouTube channels. They've decided to invite me on their show tonight, so apologies in advance. But if you are around tonight at 7 o'clock, feel free to join us over at Pusa Studios on YouTube, and we'll talk more over there. Let's see. Oh, yeah, thank you, Neil. And if you're willing, if you are willing to share this out on Twitter or let folks know, please do. Your Real Estate Whisperer, I thought the volume was better before. Okay, so what would you say now, Your Real Estate Whisperer? Is the volume okay now? I think I turned the knob down the wrong way. Okay. Let's see. How about now? Is that any better? And I'll go ahead and get rid of that. Did I turn it down? Okay. Can you hear me now? So let me do something here. Still fiddling, still learning how to do this thing. Okay, we getting any better? I know it's about a 20-second lag. Thanks. Okay, cool. Oh boy, much better, much better. Great. Okay. I hope anything that I have been talking about still managed to get through. But if it didn't, kindly let me know. And if I have to, I can always go back and discuss it again. But if that was otherwise okay, maybe just a little bit faint, then fine. Can you hear me now then? Right. So let's see. So Crypto is asking me, Crypto Cruising wants to know, what are my thoughts on what SpaceX are doing compared to NASA? Well, I mean, I think that's kind of cool. I think SpaceX, I'm a big fan of what they're doing. At first, I will tell you, I was very, very skeptical of the whole idea of commercial launch. But it seems to not only be a good idea, but a great one, because what NASA has effectively done is they've said, listen, we acknowledge that we tend to become a lot mired in our, bureaucracy and so forth, and things can get a little bit slow and expensive. Okay, I won't touch anything. Thank you, Circusy. So let's go ahead and let the private sector see if they can come up with ways of doing it cheaper and more efficiently. After all, they have fewer people to answer to, a little less paperwork, and SpaceX have proved that idea correct. It is really, I think they've just done a wonderful job, and I think that what NASA is essentially trying to do as far as human spaceflight, what they are trying to do is, say, hey, we have a space station, it needs to be resupplied. We have astronauts up there. We need to get people up there and back and so forth. SpaceX, you take care of that. We're going to go build this other great big rocket called the Space and Launch System that will take us to Mars. And SpaceX is going, okay, cool. Yeah, all right. We'll be your taxi service to the space station. Oh, by the way, while you're doing that, we're going to go ahead and build our own rocket called Starship, which will take us to Mars. And that's really what they're doing. And I got to admit, I think SpaceX has a far better shot at success than NASA. Don't get me wrong, I'm a huge NASA fan. I think NASA's specialty is in doing the kinds of things that don't make any sense from a business standpoint. You know what I mean? So they don't have any, in other words, let's say building the Hubble Space Telescope, for example, or the James Webb Space Telescope. That's fantastic. That's exactly what they should be doing. You know what I mean? They should be, investing in science and making it possible for us to do science and to understand the universe. There is no profit motive to building a James Webb Space Telescope. But if there is a profit to be made in sending people up to space or resupplying the space station, or even ferrying people back and forth to and from Mars, yeah, I think that's entirely appropriate. Anyway, long answer for your question, but that's generally my thing. I think I saw a super chat. Oh my gosh, another one from Create You. Matt, thanks, dude. Got a long drive ahead of. Is colonization of Mars reality in our lifetime? How do you think we can build more investor interest? What's the biggest challenge? Okay, I got to put that up there, right? Thank you, super chat, Matt. You're cool, man. Is colonization of Mars a reality in our lifetime? Gosh, yes, it's a possible reality, but I do believe it is something that we should expect to see within our lifetimes. Technologically, we're not there yet, but we can get there. We know how to get there. We know there's a long road ahead of us. You're absolutely right, but I think it is entirely possible within our lifetimes. I think, however, it's going to depend a little bit on how we consider colonization. In other words, are we defining colonization as a sustained, self-sustaining colony that will be able to thrive and survive without so much as a single packet of chips from Earth being sent? Maybe not. Probably not within our lifetimes. But certainly, as far as setting humans on Mars and resupplying them, yeah, I think so. Now, for my students, I think within their lifetimes, then yeah, they can see a self-sustaining Mars. I think that's entirely it. But the biggest challenge, right? I mean, how do you think we can build more investor interest? I think, again, I'm not a business person. I'm not a businessman, obviously, but I would say as far as building investor interest, and I'm sorry, I don't really know how to resize these chat windows. Oh, look at this. Look at this. I can resize the chat windows. So how do you think we can build more investor interest? I think that's really going to be like, okay, hey, there are X number of resources, and as the cost of access to space dwindles, I think then there becomes a profit motive to getting there. So what's the biggest challenge? Getting there. Just getting it done, being the first, and making it viable. Terrific questions, Matt. Thank you. I hope that provides at least some context to your question, if not a full answer. Oh boy, see, talk about business opportunities. I want to be the first realtor there. There you go, Christina from Your Real Estate Whisperer. You can be selling the first bit of Martian real estate. Don't expect to make a lot of money because you can't grow anything there, but you got to start somewhere, right? You got to start somewhere. There's no water. The atmospheric pressure is about 1/1000th that it is here on Earth, so basically it's going to feel like a vacuum. You're going to die of cancer because of all the extra ultraviolet radiation, and you won't be able to breathe, and there's no water. So I'd start low. I would go maybe like 10 cent, per hectare and go with that. Hey, Patty Broussard, how are you? It's wonderful to see you. Oh gosh, and let me kind of just keep working through here. I just want to make sure I'm addressing my students. I got to make sure I'm taking care of them because I love my students more than they'll ever know. Nah, it's fine. A lot of people think David Sims says a lot of people think the average speed in an elliptical orbit is the speed when the separation between primary and satellite is equal to the orbit's semi-major axis, but that is not correct. Speed when the separation between them. Okay, yeah, I mean, the average speed, yeah, you really have to integrate it over the entire orbit. You're absolutely right. Average is a nice hand wave way of saying it, but you are right. You are going to have to integrate as you go completely around the orbit. Well done, Dave. Well done. All right, so let's see. Moser, is that Maslow? I forgot. Maslow said he was here earlier. One of my students, but anyway. Let's see. Question. Are we living in a 3D space or a 4D space? Wow, that's a very interesting question. So we know that we live in a universe that has three spatial dimensions, at least three spatial dimensions that we can easily identify. But then there is an additional additional dimension of time, right? So you can say that we live in a 3+1 universe or a 4D universe, if you prefer to throw that single dimension of time in there. The catch with time is that it's linear, right? You only go forward in time. That means we should be able to go backward in time, but it looks like physics won't allow that, but there's no sideways in time. So there you go. However, if you delve deep into M theory and string theory, they think that, well, you know what, there could be as many as 11 dimensions. I think it's 11, but the other dimensions are so tiny you just don't get to see them. They're not perceptible from us. They're not perceptible to us, so we can't see them, let alone move toward them. But that would explain so many things. So, yeah, it's an interesting question. And, I'm more of an observational astronomer to the extent that I've been doing research. It was all observational based, and this is stuff that we cannot observe. There's no experiment that we can really do except for building like an enormous. We have the Large Hadron Collider. How about the Are You Freaking Kidding Me Hadron Collider? Something like that might reveal those extra dimensions. Let's see. Oh man, Christina is killing me with the super chats because will I be creating study guides for my students? um, I don't know what a study guide is. I think I'm doing that. I think I give them that. See, if in my class I provide PDFs of all of my presentations. I also have in my class, we use a system called Blackboard, if you guys have ever heard of it. So I even have videos, like all videos, where I'm lecturing and basically presenting the conversation again for them, so they can effectively hear the same lecture twice or three times. They can also You can also take the quizzes. You can also re-practice the online quizzes, which will help you to study as well. So I think that's a study guide. I think Blackboard is our study guide. Anyway, I don't know. Thanks for the super chat, though, Christina. Wow, it's so cool. You guys are so cool. You guys are awesome. I love you guys. Oh gosh. Okay, so do I believe we can encounter other dimensions, such as during an out-of-body experience, etc.? Insert. I'm a deadhead, so insert a joke there. As far as seriously encountering other dimensions, I don't know. I don't know. That may be a issue where our brains are only wired a certain way, to the extent that extra dimensions are imagined. You might say they're all mathematically imagined. In other words, they're all created as a result of the maths, which is why it's easy for physicists to discuss higher dimensions, because they're not trying to envision them. They're not trying to imagine what direction you'd have to go to reach those extra dimensions. So they're mathematical constructs, and it turns out when you employ those mathematical constructs, you solve a lot of questions. You answer, or you address, at least I could say, you address a lot of questions, and some things that were previously irreconcilable begin to make sense. However, I'm not a theoretical physicist. I'm going to have to plead a little bit more ignorance there. If there's an observation that we can do, that we could test this with, I would be just thrilled if that were possible. So I would love to know. I would really love to know, Jax Dia. Thank you so much for that. And holy camoly! Oh, classical muse. Wow! Just because I love science. And I love you. Thanks, man. Or thanks, man, woman. Thank you very much. Wonderful person. Oh, thank you so much for that generous chat. Oh, my God. You guys are fantastic. You guys are just way awesome. Holy cannoli. Let's see. Question 2, follow-up. If space is only 3 real dimensions, shouldn't there be an actual center of the universe? Wow. So 3 real dimensions. So I think what you're saying are 3 physical dimensions. At least, no, let me back that up again. 3 spatial dimensions, right? So if there's 3 spatial dimensions, is there in fact a center of the universe? No, but I know where you're going with this, right? Because, well, okay, this room has 3 spatial dimensions, right? And there's a center to this room. The way to think a little bit more about this is the fact that, if one way of considering the shape of the universe, since we are not able to put our minds in more than 3 spatial dimensions, is let's just go ahead and just subtract one of the dimensions of space, right? Let's get rid of height. Let's just make our lives a little bit easier. That way we have a nice flat 2-dimensional universe. There's a couple of different ways you can envision this, but one way to think about it is a stretching sheet, right? You just imagine this thing stretching. Another way you can imagine it is you can imagine on the surface of a balloon that's expanding. Now all of a sudden there's a 3rd dimension, right? But that dimension is not in the physical spatial dimensions of the universe. The spatial dimensions of the universe are the surface of the balloon. Okay, so in other words, there could be another higher dimension, but even that's not a very good analogy, because that implies that the universe is expanding into something when in fact the universe is not. It's actually expanding into itself. I know, kind of weird, isn't it? So yeah, we really don't have a simple model to translate into, so we have to use all these alternative models to help describe different aspects of it. Probably the best model of our expanding universe that I've heard of is, imagine you are a raisin inside of an infinitely large cake. There's cake everywhere. So cake is space, okay? And if you bake a cake, cake rises a little bit, right? So it expands. Imagine if you look around, you, the little raisin being in this expanding cake universe, you look around and you see your fellow raisins, So the universe expands, but the universe is infinite, right? And that's the key thing. The universe is infinite. So where is the center of an infinite cake? And the answer is nowhere. Likewise, where is the center of an infinite universe? The answer is nowhere, right? So there is no such thing as a center in an infinite universe. And everything that we've been able to do, every observation we've been able to make, every investigation we've done, these are things that we can test observationally. Everything that we've been able to discern just implies over and over and over again that, yeah, the universe is basically infinite. In which case you cannot have a center. So there you go. So there you are. You're a raisin in the infinitely expanding cake. That means the other raisins are getting farther and farther away from you as the cake expands and takes away everything. Well, it's the same thing with the universe. The universe, space is expanding, and it's carrying all those galaxies away from us. It's not that the galaxies are moving through space, but rather space itself is expanding like the baking cake. So have some cake, some nice vegan cake, and enjoy your expanding universe. Thank you, though. It's a pretty cool question. I like that. So let's see. I think oh my God! Oh, geez, Patty Broussard. Thank you. Thank you so much. Thank you so much, Patty. Oh, you were wonderful. I don't know what to say except you're awesome. You're just amazing. You guys are just wow. Surrogacy, I still don't understand multidimensional stuff. Yeah, neither do I. Honestly, like I said before, these are mathematical constructs that help us to put everything together in a model. But you're right; it's not something that's easy for us to grasp mentally, unless maybe you're like Hawking or super genius. But yeah, so we use these models, we use these analogies, we come up with these little hacks of working around and understanding some of these things. Thank you so much, Patty, for that super chat. And I just want to make sure I haven't missed anything. And, oh, man. Yeah, Matt, thanks, man. You hitting it again? Holy cannoli. I'm asking all these questions because I love your explanations. When will we leave standard propulsion systems behind us? What's the next step? Gravity? Light? Okay, well, sure, let's talk about propulsion. Why not, right? It's not really astronomy, but hey, we want to explore the universe. Matt, I don't know. I think, here's the thing. Chemical propulsion is still the biggest bang for the buck, all right? In other words, you can generate a lot of energy and you can throw that fuel out the back of your rocket nozzle very fast and very hard, okay? And Newton's third law of motion says that for every force, okay, there is an equal and opposite reaction force, right? So in other words, when you push the fuel out the nozzle, the fuel pushes back on you, right, and shoves you forward, and that is. And so the question is, okay, what can I push out the back nozzle that is energetic enough to accelerate me as quick as possible? And right now, the best game in town is a chemical rocket, right? That is your best way to do it. However, chemical rockets are not very efficient. You burn that fuel very quickly. And that means if you want to burn your rocket longer, you have to carry more fuel. If you carry more fuel, now your rocket is heavier and is more massive. Now you got more mass to push, and you can't accelerate as quick. So what we have been able to do is employ other propulsion systems that are not chemical-based. And specifically, I'm referring to something called the ion engine. So an ion, okay, just remind ourselves what that is, right? You have an atom, and it's got a nucleus, okay, and that nucleus has one or more of these positively charged particles called protons, and it may have some non-charged particles or neutral particles called neutrons. So the protons and the neutrons come together to form a nucleus, and then surrounding the nucleus is a cloud of these negatively charged electrons, right? And that's where we get electricity from. It's flowing electrons. So what can happen is if you can give this atom, right, the nucleus and the electrons, enough energy, you can get one or more of those electrons to strip away off the atom. When you have an atom that is missing electrons, the atom is now positively charged. We call that an ion. Okay, so ions are cool because ions have a positive charge. That means you can take a magnetic field and you can make those positively charged ions flow along that magnetic field. It just follows those lines. It just goes. Hey, you know what you can do? You can accelerate those ions out the back of your ship. In other words, you can push those ions out the back of your ship, and the ions push back on you. And so you accelerate forward. That's thrust. That's how an ion engine works. I think the gas that's used in those ion engines is typically xenon, I believe, if I remember correctly. Anyway, those ions, those xenon nuclei are heavy. They're massive enough that they can give a reasonable push. But the push that they provide is equivalent to, and I don't have one with me. Oh, here we go. The push that they provide is equivalent to the weight of this tissue resting upon my fingertips. So the pressure and the weight that the tissue is putting on my fingers is roughly equivalent to the thrust, to the force that the xenon atoms can apply. So that means that you accelerate, but you don't accelerate very much. So why on earth would we use something like this? Well, you obviously aren't going to get off the surface of the Earth using such a rocket engine, right? You're just not going to get the thrust needed to escape Earth's gravity and get into orbit, let alone escape velocity. So what are you going to do? Well, you're going to fire your rocket using a chemical engine to get you out there, separate from the rocket, and then once you're in space and you're free of any strong immediate gravitational fields, then you fire that ion engine, and then you slowly... Sergey says it's not magnetic field that accelerates electrons or ions, but electric field. Yes, I'm sorry. Did I say magnetic field? You are right. My apologies. It's an electric field. Sorry. Bad astronomer. Then you can accelerate your ship forward, and we've actually done that. We've done that with the Dawn spacecraft, which was the first spacecraft in history ever to visit one body in our solar system and then break orbit and then visit another body. So it was Vesta in the asteroid belt and then off to Ceres. Anyway, so we are doing it, Matt. That's a short answer to your question. Light sails, solar sails are other technology. These are other technologies that are being tested right now. So I think, the short answer is yes, we are using it, but I don't see us eliminating the need for the chemical rocket anytime soon. Cool stuff, though. Let's see. Will I be doing T-shirts to sell on the channel? Okay, I think that's been addressed already. And thank you. And Andrew Kroll. Wow. Hey, Andrew, thank you so much. Thanks, man. That's awesome. Thank you, sir. Super chat from Andrew Kroll. Particle accelerator in space. Any advantages? Andrew, that's an interesting question. I think probably the best advantage to a particle accelerator in space might be that you could build it larger. In other words, you're not having to excavate, underneath mountains and things like that. So in some respect, it might be easier, but I mean, really put that in quotes, italicize it, etc., because I don't know. I think it would be very challenging. But I think the thing is if you could build these rings larger, then you can accelerate particles to higher energies. And if you can collide them at higher energies, we can find out new things. Because the Large Hadron Collider, I'll just say this very quick, has been a little bit of a bust. And I don't mean that in a disparaging way. That's more of a factual way. The Large Hadron Collider in 2012 demonstrated the existence of the Higgs boson, and I won't get into all what that's all about right now, but it found that that was effectively why it was built. That was the main question I was trying to answer, but it hasn't discovered anything since. And I think the only way we're going to be able to see anything beyond the Higgs is to build a much, much larger collider. So maybe space is the way to go for that. But thank you so much, Andrew. It was a fantastic, generous super chat. I think I had a... okay, so Robin asks, okay, can you give me a refresher on Kepler's laws? Sure, Robin. Yeah, let's go ahead and take a quick look at Kepler's laws. Make sure we're completely one with all that. And again, I'll try to do this, show, not tell, but not turn it into a, stupid, boring lecture. It's not what you showed up for. Okay, Kepler's laws of motion. So we gotta get that to download first. But anyway, while that's downloading, the idea behind Kepler is that he was a mathematician that Tycho Brahe hired, and that's because Tycho Brahe had this idea of how the universe he thought should work, and Kepler was able to demonstrate how planets, at the very least, orbit the sun. So the first had to do with the fact that let me go ahead and just bring this up here. Let's switch over. All right, so the first law, remember, is where Kepler discovers that planets are always going to orbit the sun in an ellipse. Okay, now prior to this point, the reason why this is a big deal is because we're in the Dark Ages, and people thought, oh, this is this means that God created these orbits and they have to be perfect circles. And we learn that a circle is a special case of an ellipse, but the fact of the matter is that planets follow these elliptical paths around the sun. So the key thing is that you've got the sun at one focus, right? So you have the sun, you have this little blank circle, all right, in the middle of your ellipse. So those are the two foci, right? And folks, if you haven't seen the prelude to this, the idea is that if you take like a couple of nails, right, and wait for my beach ball to stop here, but if you take a all right, we'll just let it do its thing. Sorry, I'm getting a little excited with my keynote. Sorry, guys. All right, so if you take two nails, right, and you hammer them into the wall, and then you grab your pencil, right, and you tie a piece of string around the pencil and the nails, and then you do what comes naturally, you get an ellipse. So the 2 points where the nails were are the two foci, or focuses, right? So you can take an ellipse, you can go across the fat end of the ellipse, and that gives you the major axis. But then you can take 1/2 of that, and you'll get what's called the semi-major axis, okay? So we were discussing orbits earlier, and we were discussing eccentricity. I'm just going to step through here. But the eccentricity is just a measure of the fatness of the ellipse. Okay. So what Kepler discovers is that, yeah, it's planets are following this ellipse. The sun is at one focus, nothing at the other. We also learned, by the way, that there's a close point. There's a close approach point to the sun. That's our perihelion, right? So that's Latin for peri, as Latin for closest, helion, or actually Greek, I think. I don't remember if it's Greek or Latin. Any scholars? Anybody who knows this stuff? Anyway, perihelion means closest to the sun, whereas aphelion is farthest from the sun. Now, the perihelion and aphelion are less important than just understanding that it's the planets following those elliptical orbits around the sun. Now, the second law he discovers is that, well, when the planet's going around the sun, if you were to measure an interval of time, right? So let's just pick a planet, let's call it day 1. And then we have the planet swinging through, in this case, swinging through perihelion. So we arrive here at day 10. Let's compare that to the same thing, another 10-day interval, but this time at aphelion, right? So we have another 10-day interval. So you see we have a couple of dots and we have our sun, right? We have 2 intervals around the sun. So if we do what comes naturally, and we say that the time intervals are equal, right? If we were to measure the area and play connect the dots, we've discovered that both of these areas are equal. So Kepler is saying in the second law that a planet sweeps out equal areas in equal intervals of time. And that's a key thing, because it means that the planet has to be moving the fastest, right? It has to be moving relatively fast on the interval on the left, and it has to be moving slower on the interval on the right. So the speed, the velocity of the planet changes, it varies. And we also learn that a change in velocity is acceleration. That means that the planet is accelerating to the sun. Kepler didn't really understand the fine points of acceleration versus velocity. All he knew is that, hey, what do you know? The planets all seem to be sweeping out equal areas at equal intervals of time. So Kepler then has his third law, all right? And he basically, to understand his third law of motion, we have to take into consideration two factors, right? A planet has an orbital period, and it also has an integrated distance from the sun, right? But average distance from the sun, the semi-major axis. And it turns out that if you take the value of the orbital period and you square it, it's going to be equal to the cube of the semi-major axis. Quick example, right? Let's just consider Earth, for example. Okay, it has a period of 1 year. That means it also happens to have a semi-major axis of 1 astronomical unit. So you have a P of 1 and a A of 1. So let's take P and square it, and we get 1 squared is equal to 1. And we take its semi-major axis and cube it. 1 cubed is, 1. So 1 equals 1. But if you want to be a little bit better sold on the idea, let us consider, let's just say Jupiter, right? So we could even take the orbital period of Jupiter, and you could see it's just under 12 years, 11.9 years. But it has a semi-major axis of a little over 5 AU, 5.2 astronomical units to be exact. So now, what happens if we take the orbital period of Jupiter and we square it? Well, now you get, 141, squared years. Let's forget the units. 141. That's actually equal to its semi-major axis, right? 5.2 cubed is 141. So there you go. Those were Kepler's big discoveries, that there was this uniform relationship. And if you look up the orbital period of any planet and its semi-major axis, and you square the former and cube the latter, the results will always equal one another. So those are Kepler's 3 laws. Let's see. First things first, Robin, does that address your question? I want to make sure I got you, right? So how do I get this thing going on here? All right. So let's see. Okay. I'm just taking a look here, and Andrew. All right. Oh, whoa, Eddie Smallhorn, dude, man, holy moly! Thank you, dude. Peace. Wow, you guys are helping me to pay my mortgage. No, but really, I'm very grateful. You guys are so generous. I just made the IQ level of the stream go down. No, you did not, Eddie. Come on, man. You're a good guy. You're all right, Eddie. Thanks, brother. Appreciate it. Okay, question 3, follow-up. Nice cake analogy, going back to our expanding universe. Thank you. I like cake, too. With 3 spatial dimensions, shouldn't at the Big Bang all raisins be in one place? Wouldn't this place be considered the center, where all raisins once were? I know exactly where you're going with this, right? Yeah, it seems to imply that there should be a center. But again, here's the catch. Remember when I said the universe is infinite? That means it was infinite even at the moment of creation, right? And that's the thing. Big Bang, we got to be thoughtful as to what we're thinking about. What we're really talking about is a moment of infinite density, right, where everything was brought together, and yet paradoxically, it was also infinite in size. So just imagine all those raisins being, as you say, brought close together, and then over here are all these raisins brought close together. Over here, all these raisins are everywhere. The universe is just one giant compressed raisin, right? That's what we started with, and then it quickly, instantaneously, all those raisins started moving apart from one another. So it's kind of strange because we're dealing with both an infinitely dense yet infinite sized universe. But that's the universe at the what's called the singularity, when the universe was created. So I hope that addresses your question. But yeah, there is no center, even in an infinitely dense universe. How weird is that? Oh my gosh! Wait a minute. I saw it. Oh man! Oh man! Oh man! Oh man! Oh man! Jeez, I can't believe this, Matt. You're oh man! Great conversation with the rise of flat Earth types. Do you believe scientists such as yourself can do a better bridging the gap and partnering with them? To tell you the truth, Matt, I don't think they want to hear from us. You know what I mean? Their position is fundamentally anti-science. They believe that science is arbitrarily hard and difficult. That it's a way of separating the smart people from the rest of us. That the universe is much easier to understand than those scientists are making it out to be. They're only doing it just so they could justify their funding, And here's the thing. If that's the way the universe worked, right? If the universe were flat, for example, we'd be saying, okay, cool, guys, it's a flat Earth, not to be confused with a flat universe. Okay, flat Earth, right? And that's what we would go with. If the universe were that easy, then that's the way it would be. It isn't, It isn't. It operates differently. And so I think the main argument that you'll hear among flat earthers or electric universe proponents or whatever is that this is way easier to understand and making it harder to be, and all we have to do is just know the truth. Here's the deal, though. I'm sorry, I'm going to repeat myself. So let me just say what I want to say here. If the universe is the way it is, and it's not up to the universe to be easy for us to understand. It's up to us to understand it. So the universe is going to do what the universe is going to do. Our job is to understand it, and we have the curiosity and the will to do that. So if you have that curiosity, you will develop the mathematical skills and tools necessary. Okay, it wasn't like we woke up one day and said, "Hey, let's invoke a bunch of strange maths to make things seem more complex than they really are." No, it's more like this is what we have to do. Okay. Andrew Cole is saying, I think he means science and educator partners. I'm sorry, I went off on a bit of a rant there. My apologies. Yeah. And Andrew also adds, but they already do. Yeah, and you're right. There is a lot of partnerships with science and educators. So yeah, that's it. But anyway, I hope I was able to address that. Thank you so much for the super chat, man. You're awesome, dude. Hey, I want to welcome Beanie Draws. Beanie, hey students, I've been telling you about my friend Beanie. Beanie Draws here. This is my friend in Australia who tells me what the Southern Cross looks like, so I know how to describe it to you, because he can see the Southern Cross and we can't, because we're up here in the Northern Hemisphere. How you doing, Beanie? Good to see you, my friend. Let's see. Hey, you do it is here. Oh my gosh. Hey now, it's been since 1993 since I had dynamics. Welcome back to 1993, my friend. It's great to have you here. I really do hope that I'm addressing everybody's questions, comments. there's been way more than I expected to be. I'm grateful, but I want to make sure I'm helping my students, because I do see something here. Oh, okay. I'm scrolling through here. Rachel Talbert said, "Can you go over apparent solar time again?" Okay, so first of all, Rachel, just to let you know, the expanding universe is not on the exam next week. Okay. All right. Let me try to yes, Andrew, I can read that. Anyway, let me address your question about apparent solar time. And hey, you know what? I actually called this live stream "How the Sky Works." So this actually has something to do with the sky. All right. So here we go. Back in the keynote. Let me just go ahead and bring up that presentation so I can show rather than not tell. This is fun, guys. I'm really enjoying myself. I hope you are too. You guys are just wow. All right, I'm gonna make this like a regular thing. I promise. This is like a thing now. Okay, so I was talking about time, and I gotta wait for my keynote presentation download. So keynotes are all stored up in iCloud. So that means it's great because it keeps it off my hard disk. There's only like 256 gigs of RAM on this thing, gigs of hard disk space. So it's a good way to keep stuff, keep the hard disk tidy. But what I think we were talking about, oh boy. Let's step through it really quick, okay? And let me switch over here to my bit about time. So what's going to happen is when we look at how everything's working, okay, here's our sun. If we could turn off the atmosphere, okay, I chose this particular date on purpose because on this particular date from Baltimore, okay, the sun was right on what's called the meridian, right? It's that imaginary line that runs directly from due north all the way overhead to the zenith, all the way to due south, okay? So that's our meridian. So the sun happened to be right smack dab there on the meridian at exactly 12 noon local time. Yay, all right? But what's also happening is that the Earth is going around the sun, right? So if we allow the Earth to make one complete revolution around the sun, okay, you notice that when we come around one Earth revolution later, oh, and I should preface this by saying, let's just take note of where the stars are. Okay, you notice that the stars are all right here, right? And there's an arrow pointing in the inset here. There's an arrow that's pointing to the stars. It's pointing to the sun, but it's also pointing to the stars behind it. So watch what happens as we let the Earth make one complete rotation on its axis. Okay, well, it makes a full rotation on its axis. The arrow is once again pointing at the same stars. So the stars have returned to exactly where they were one Earth rotation ago. But you notice that the sun has not yet come to the meridian. So if you look at the interval of time, right, we started this on the 12th at 12:00. It's now 11:56:0, right? So this rotation with respect to the stars is called a sidereal day. All right, sidereal literally represents, it's Latin for star, right? So it's with respect to the stars. So it's 23 hours and 56 minutes. Now, that is how long it takes for the Earth to make one rotation. But the sun is missing. The sun is off target, right? We got to get the sun back on the meridian. That's what we want to go for here. So we're going to let the Earth rotate just a wee bit more, okay? And it's it's going to let the Earth rotate just a wee bit more, and now the sun returns to the meridian, right? This is a solar day, okay? This is one rotation with respect to the sun, 24 hours on average. On average, and I'd like to just quickly address this on average business, okay? Because we've got a few things to think about. If you're trying to rely on the sun as your timekeeper, you're going to have some real complications because, when the sun is on the meridian, all right, there are times when it's not on the meridian, it's anti-meridian. Okay, so that is what we abbreviate as AM. And there are times when it's past the meridian or post-meridium, and we call those p.m., right? So you may have heard about those terms, right? And then you've also got another complication. The sun doesn't always end up at this altitude, this angular height, this height above the southern horizon. Sometimes it's higher in the sky, right? So here's the sun on the summer solstice, here's the sun on the equinoxes, here's the sun at the winter solstice, right? So the idea is that these solar days will vary, okay? The sun rises at different times of the day, sets at different times of the day, and yes, it will arrive on the meridian. It will transit the meridian different times of the day. So, I've got a split screen here, and if you look along, there's a light blue line in both images. All right, so there's a light blue line at the bottom of the top image, and there's a light blue line horizontal across the middle of the image. Both of these represent the Earth's equator projected onto the sky. So we call this the celestial equator. And notice that I've chosen two different times. I've chosen the summer solstice, and I've chosen the vernal equinox, right, when the sun has arrived, the summer solstice, when it arrives, its northernmost point above the equator, on or about the 20th of June, and then on or about the 21st of March is when the sun hits the vernal equinox. The red arrows represent how much the sun will travel from one day to the next. But you notice, if you think about how far east it goes, in other words, how far to the left in these images, it doesn't quite cover as much eastward or leftward distance when the sun is near the equinoxes, because the sun is traveling a little bit north. At the same time, it's traveling east, right? So this means that some days, what this means is that throughout the year, the length of the solar day will vary, okay? And this is the key thing, right? The sun is not always going to hit the meridian. It's not always going to arrive at local noon on the meridian every day at 12:00. It's not going to happen. Sometimes it arrives a little early, sometimes it arrives a little late, and there are all sorts of real-world complications. But when you imagine the sun and you just sort of take, a time lapse of all of its positions, like one day to the next every 24 hours, you get this pattern, right? You find that sometimes the sun is a little early, sometimes the sun's a little late, sometimes the sun is, boom, right there at exactly 12 noon. What you're seeing is a time-lapse movie of the sun every day at 12 o'clock for a whole year. By the way, this path is called the analemma. Okay. Back in the day, right, today we measure time using atomic clocks. We have these ultra-precise methods of measuring time. But way back in the day, it was a sundial, right? And so you use the shadow cast by the stick that's toward the top of your image. It's called the gnomon. Not a gnome. It's called a gnomon. Trevor, I'm talking to you. Anyway, so this was how you would tell something called solar time. So really what we are talking about when we have a solar day, sometimes the sun is a little earlier to the meridian, sometimes it's less. We are really properly talking about something called a mean solar day. We're talking about our 24-hour interval is properly termed a mean solar day. We're taking the mean average, you might say, of all of those solar days. Sometimes the sun is a little early, so it's going to be a little more than 24 hours. Sometimes it's going to be late, so it's going to be a little less than 24 hours. So you add them all together, take an average, let's call it 24 hours. That's basically all a solar day is. Let me just verify I've addressed, I hope I'm addressing the question. But in any event, just to kind of finish the thought here, solar time is going to vary with longitude. So I've got a sundial at Towson University in Baltimore. Go Tigers. I've got another sundial over in Pittsburgh. And if you look, you'll see that the shadows are different, right? Because the sun angle's different, and it's even more different out there in Ohio. I think that's Cleveland. I can't remember. Cleveland or Cincinnati. I'll get in trouble. Even Frederick, right, Maryland, which is just an hour west of here, even they're going to have a slightly different time when we are recording something called 12 noon. And in Philly, you've got an earlier time. So this whole notion of using the sun as your timekeeper is a really bad idea for for these reasons. That's why we have time zones, and it gets into a great big mess after that. But we basically now track our time according to atomic clocks. We don't bother using the sun as our timekeeper anymore. All right, Rachel, I hope I got your question addressed. Kindly let me know if I have not. I want to make sure I'm taking care of my folks here. Rachel, no, thank you so much. I appreciate that very much. You're more than welcome, Rachel. Please let me know if I can help as well. Help any further. Well, have I missed anyone else? So I was reading this generous super chat, then I found Rachel, and now let me see here. I'm just quickly going through. Apparently IQ means everything. Why do you say that, Quintus? What does that mean exactly? How do you figure? Let's see here. Oh, my mother-in-law, of course. Yes, hi, Mom. Don't have to buy a shirt. Don't buy a shirt, Mom. Very nice, very thoughtful. Appreciate it. Let's see. Just going through all this. I missed Crypto's last super chat. Oh, did I? Okay, I'm just scrolling up here. Oh man. Oh, £4.99. Christian's fantastic. Thank you, Neil. Appreciate it. Love you, man. That's so nice. You guys are just this is so cool. You guys are just so nice. I mean, it's not like money, but it's like, hey, you're showing this genuine appreciation, and I'm genuinely grateful for you. I really am. Wait a minute. Andy Law, I'm from Edinburgh. Awesome. Studied undergrad physics alongside Peter Higgs. Dude. But my dad worked at Edinburgh Physics Department and knows Peter Higgs to speak to. Still blows my mind. Oh, that's so cool. That is so cool. I would say tell him I said hi, but he'd be like, let's see. Oh, Christopher Cassidy, love your channel. Thank you, Christopher. Appreciate it. I'm glad you're here. I'm glad you're enjoying the content. Thank you. Let's see. Just gotta. Again, I know I hate watching live streams when when it's always like watching somebody read the stuff. I'm just trying to make sure I'm getting my folks covered here. And let's see. I think I've addressed everyone else. If I haven't addressed your question, go ahead and go ahead and put it here. Boil Nuts, hey, how you doing, Boil Nuts? Your opinion if the sun has or will experience a micronova. Okay, I have to admit, I don't think I really know quite what a micronova is. I haven't heard that term before. We'll see. But if I could say this, the sun will evolve, and the sun will experience what's called a helium flash. That's a very explosive event. In fact, when the sun does this, it will unleash as much energy as every star in the galaxy combined. Only, it will not be visible from outside the surface of the sun. That's because the core absorbs 100% of that energy. And that's what kicks it off into a second, that's what kicks it off into a new phase of its evolution. So I'm going to talk more about that in a future video. I don't expect the sun to ever go through an explosive event or even an eruptive event such as a nova. It will expand. It'll become very, very large and very cool, so it'll become what's called a red giant. Then it will shed more and more of its atmosphere. It'll shed more and more mass until the sun just kind of whittles away, until all that's left is just the core of what used to be our sun. And then that core will shut down. and it will just continue to cool down over time as something called a white dwarf. So our sun's death, or our sun's evolution and eventual death, is more of a whimper than with a bang, even an eruptive event such as a nova. Let's see. Okay. Going to, oh, yeah, you're welcome, Matt. Thank you. I thank you so much for doing that. I really appreciate that, and then he kind of follows it up with, wish I lived closer, I'd take a class to expand my brain. Thanks, dude. Yeah. Then I can't imagine I would be able to fill that wonderful brain of yours, dude, but thank you so much. Let's see. Fraley asks, what's your take on the Big Rip? Wow, yeah, that's one of the many end state scenarios of the universe. So this question, I think, is based on the notion that, well, the universe is expanding, but what was discovered back in 1998 is that the universe is expanding, and the rate of expansion has been increasing. So that implies a scenario where, maybe there will come a time in the deep, distant future where space will be expanding so fast that everything will come apart. Not only will the galaxies have just gone beyond our cosmic horizon, even the Milky Way will tear itself apart, and all of the stars in our Milky Way will be scattered beyond the cosmic horizon, and maybe even matter itself will eventually be ripped apart. I don't know. I don't know if that's in fact what's going to happen. I think there are other ways for the universe to die, including what's called the heat death, or the big chill, where basically there'll be no more thermal motion anywhere in the universe. Everything will cool down to effectively zero, and without any motion, without any thermal activity, there is no more entropy in the universe. And without entropy, there's no more arrow of time. So in effect, time stops, and things cease to exist. So I don't know. That's a very good question. I really don't know the answer to that. If it'll be a big rip, or if it'll be a big chill, or if there will in fact be a big crunch. I'll try to make a video about all the different kinds of Andy Law says, "Hey, Christian, I did my astronomy course under Malcolm Longhair at Edinburgh." Oh yeah, he's one of the big guns in the business. Oh yeah. If I can, let me go ahead and just quickly jump down here. Oh, Patty Broussard has demonstrated something very cool. I stood an egg on its tip during the vernal equinoxes one time and stayed standing for 2 weeks. I put cans around it to protect it from getting knocked over. Cheater. Yeah, you probably heard that myth, right? Oh, if you stand an egg on its end on the vernal equinox and you're on the equator, it'll stay perfectly still. No, it will not. Oh my God, Aaron Wilson! Holy mackerel! Thank you so much. You're awesome. Thank you so. $20. Whoa, dude, this is amazing. Thank you. And Erin, by the way, she's a patron supporter. So is Neil. So is Patty. Oh man, you guys are the best. I love you guys. Oh boy, okay. Oh man, and then and Beanie, look at you. I can't believe you, man. Thanks, brother. Appreciate you, man. I really do. Thank you so much. And Beanie, it's my dream to come and visit you because I want to see the Southern Cross. I really do, and I hope you'll show it to me. I hope you'll point it out to me in the sky. Thanks, brother. I appreciate you, man. Oh man. Okay. Oh, Stuart Smith. Oh, thank you, Stuart, for dropping by. It's so wonderful to have you. Let's see. Okay. Can I address this one? Okay, question 4. Thanks for letting me think more of the dense raisins. In the meantime, besides galactic redshift, what other direct observational evidence do we have for an expanding universe? Wow. Okay, so what other evidence do we have for an expanding universe? Well, for expanding universe. Okay, so we have the redshift. That is the number one thing. Also, the cosmic background radiation. that's another piece. That's another line of evidence. That's really more about. I'm sorry, I'm conflating two things. The redshift is the ultimate evidence of an expanding universe that I'm familiar with. I think what I started to answer there was what evidence is there that the universe had an origin, had something like a Big Bang, and that's where the cosmic microwave background radiation kicks in. As far as expanding universe, I'm really only familiar with the redshift, and for those not familiar, redshift is simply, as we look at the light coming from galaxies, their light is stretched. It's taken to longer and longer wavelengths, i.e., they get redder and redder in color. So that's really the evidence that I'm familiar with. Oh man, thank you, Joseph. Appreciate it, buddy. And Joe is a fantastic guy. Actually, his channel used to be called The Fantastic Joe. I don't know why he changed it. I love that name. But Joseph Andrews, thank you so much, my man. I really appreciate it. He's also a brilliant videographer and just has a great way of well, come on, man. I know you said to ignore the message, but thank you, David. You're very generous. I appreciate your super chat. You guys are being so generous today. I can't believe this. Holy cannoli. Quick question. Will we know the approximate dates that each of the equinoxes? Okay. This is a student question. So, will we need to know the approximate dates of the? It's a good idea to understand when they are, but here's the thing. No, I don't expect you to know it's March 20th or 21st, right? Understanding that the sun reaches the vernal equinox in March, or understand when does the sun reach the equinoxes? Is it summer? Is it in June or is it June? Is it December? Is it September? Is it March? Think along those lines, okay? So you don't need to know the exact date. So they're really not that hard. On or about March 20th, on or about June 21st, on or about September 22nd. They're on or about December 21st. But the actual dates vary from one year to the next. So no, I'm not going to hold you to those dates. But just wanted to let you know the drill there. So thank you, William, for the question. Hope that helps you out. And man, Matt, you are. Oh, brother, man, I really should be playing like There Goes My Hero, except I would get demonetized. I don't know how you do that, Matt, but holy cannoli. Last stupid question. No, it's no stupid questions. Oh my goodness. Do you see any scientific value in moon exploration? Yes, I do. But you're right. There's not as much. It's not as science. It's not. You don't expect it to be as rich a hunting ground as, let's say, exploring Mars scientifically. Probably the biggest scientific value is understanding better how the Earth and Moon formed, because the Moon, we already know, is basically made of Earth mantle, right? And so that really supports the hypothesis that there was once upon a time a Mars-sized object, which we call Theia, that smashed in to the early Earth, shearing off a huge chunk of the Earth's crust and mantle that formed a temporary ring around Earth, and condensed out of that ring is now our moon. So I would like to see more geologic studies followed up to understand that formation better. I would also like to know, does the moon still have a hot interior, even if it's a very tiny core? Is there any heat left in the moon? I suspect the answer is no, because of those huge gray maria that we see on the moon, which are basically the results of massive impacts that occurred about 3 billion years ago that just hollowed out effectively the interior of the moon. So that's a question I would like to see addressed. Can we do some lunar seismology or set up some more sophisticated, more sensitive lunar seismology experiments to see if there's any heat down there? So yeah, I do see a lot of legitimate science questions that can be answered in future moon exploration, but I also know that as an object, it's not as geologically diverse as, let's say, Mars. So thank you. That's a cool question. Let's see. And thank you again for the super chat, man. You guys are fantastic. And thank you, Fraley. Appreciate it, man. Launchpad is a great channel. I'm newbie to astronomy. Dude, anytime, man. Your friendly neighborhood astronomer at your service. Okay, okay, and hello, Launchpad Astronomy. Are you going to see SpaceX's DM1 launch tomorrow? What are the advantages and disadvantages of building and telescopes? Do you know about electric solar wind sail? Okay, cool. Yeah, really quick. What he says, right? So tomorrow morning, that's right, we were talking about SpaceX earlier. I almost forgot until you reminded me. Thank you, Raj. Yeah. You guys know what's happening tomorrow. SpaceX are going to be launching their crewed Dragon spacecraft. Now, to be clear, it's a crewed. It's called Crewed Dragon, as in CREWE. Crewed, like people, like a crew flying on the Dragon, right? Except it will not be crewed tomorrow. We used to call it manned. Okay, we used to call these manned missions or unmanned missions. But we have plenty of women astronauts now, and so crewed is a more appropriate term. It's a more accurate term. But it also, I think crude as in like CRUDE. Like I could see all kinds of snarky jokes. Anyway, they're going to be launching tomorrow. I don't know what time they're launching. What time is launch scheduled for? Short answer is yes. I'm going to watch it. Are you kidding me? I'm going to watch it. And this will be televised. It'll be streamed on the web. Like I said, there will not be any people on board. SpaceX are demonstrating their ability to launch a human-rated spacecraft on a human-rated rocket that can not only successfully launch off the pad and get into orbit, but can also successfully dock to the International Space Station using an autonomous docking algorithm. So I believe that's going to happen. Okay, so I'm hearing. So Christopher says 8:30 Norway. Is that what? Wait a minute, 8:30 Norway. Oh, that's what time it is now. But what time are SpaceX doing this? Anybody know? Anybody want to look that up? But yeah, make sure you're watching it. Go to SpaceX's YouTube channel and check it out. Or if you want to watch it with like 1,000 other people, go to Tim Dodd's The Everyday Astronaut. I saw someone say that poor Ben from tomorrow is going to be completely knackered. Yeah, it's going to be a crazy, crazy day. Okay, what other questions have I not been able to address? Students in particular. Okay, launch is at 2:49 EST. Okay, guys, so it's going to be an early morning launch. For some reason, I thought it was later. I thought it was 5. I'm glad you said that. Okay, so yeah, it's going to be early in the morning, but it's going to be worth it. It's going to be a hell of a show. Kind of sucks that they're doing a night launch. So yeah, I think at this point, wow, I thought this was going to be an hour. We've done an hour 40. You guys have been very generous, and thank you, you Real Estate Whisperer. It's my pleasure, my privilege, and thank you very, very much. Wow. NOK 50. So I don't know what NOK is. Is that... Oh, man. Well, thank you, man. Just thank you. That's awesome. 4 questions. Hey, no problem, man. I appreciate it, buddy. I'm here. I do it for free. I love talking about this stuff. Let's see. Where do I live? I live here on planet Earth. No, I'm teasing. I live in Maryland, in these United States of America. I teach at Towson University, where I teach introductory astronomy. Which is actually my favorite subject to teach. I love talking about this stuff, especially being one of the first conduits into this wonderful subject. Well, thank you all very, very much for coming by today. Thank you so much for those wonderful questions, for your generous donations. I'm extremely humbled and flattered, and thank you. You really have helped me out so much today. You guys are wonderful. I will make this a regular thing. I'll probably do this at least once a month, maybe twice, maybe once a week. I don't know. We'll see. There's a lot to talk about in this universe. I'll be more than happy to keep doing that. But I don't want to make this a long, drawn-out goodbye. I'll just simply say thank you. And to my students, reminder again, we're going to be, getting after it on our celebration of knowledge next week. Don't feel that this was the one and only way that you could have gotten a hold of me. You got my email. There's also going to be office hours next week. I'm definitely here to help you guys out. My job is to help you get smart on this stuff. I want you to be successful on this, not because you memorized a bunch of stuff, but because you understand, what we've learned. And for everyone else watching, thank you so much for joining me on this journey through this amazing universe of ours. And until next time, my friends, make sure to stay curious. Take care, everyone. Bye.